Okay, so we're going to do a couple of examples now that actually pulls in some of the ideas from friction, because we obviously want to use what we learned about in the last lesson. We don't want to just do the things we could have done in year 12, so we want to keep adding in some new things. So I've said here earlier we saw that the frictional force F was less than or equal to mu r, right? We knew that it reached that particular threshold, and then after that point, it couldn't get any more. That's why it was always less than or equal to mu r, where F is equal to mu r if the object on the plane is moving. Where the object is not moving, we saw that the force of friction acts in a direction opposite to that which it would be moving if the frictional force wasn't there. Now, that all sounds a bit confusing because it's just, I find I read that and it just doesn't necessarily make that much sense. But all it's really saying is, if something is moving in one direction, the friction is going in the opposite direction. If something was about to move down the slope, the friction would be going up the slope. If you were trying to make something move up the slope, the friction would be going down, okay? Now, one of the things here I want to talk about a little bit more, it said here, if the, what am I looking for? Where the object is not moving here. F equals mu r if the object on the plane is moving. What other scenario is F equal to mu r? Good, limiting equilibrium. If it is in limiting equilibrium, then F would be equal to mu r. Ahmed, do you remember what limiting equilibrium actually means, like in practice?
It's on the verge.
Yeah, it's on the verge of moving. It's like if just the forces changed a little bit, it's going to start moving. So we're going to do this one that's a little bit simple, which I'm going to go through relatively quickly. And then the one on the slope is a bit more complicated, and I want to spend a bit more time on that one. And then you're just going to do some practice on these kinds of things for me for homework. So a box of mass 8 kilograms rests on a rough horizontal plane. The coefficient of friction between the mass and the plane is 0.5. I always like to write that down as soon as I see it, just so I can find it easily. Find the magnitude of the maximum force, P, oh, I don't want to cross it out, the maximum force, P newtons, which acts onto this mass without causing it to move. So we're trying to say, what is the biggest thing that you could do to this block without it moving? Okay? If, first of all, for part A, the force P is horizontal. So we're going to have our normal reaction and our 8G. And we want to know, someone's pushing it with a force P, and we want them to be pushing it as hard as possible, but it's not allowed to move. I'm saying as hard as possible because we want maximum. And I'm saying it's not allowed to move because it says it's what's the maximum force without causing it to move. So how would we describe this scenario that it is in without causing to move, but still pushing it as max as possible? Good, so it's going to be in limiting equilibrium. And the value of the friction will be equal to mu r. It won't be less than mu r, it will be mu r. So I can then very quickly, rather than writing friction, I can put mu r on the diagram. I'm now just going to go through the way that we always do this. Best thing to find out first is r, then you can find out the left and right bits, because we know that it's in equilibrium, it's not moving. So first of all, looking up and down, clearly r is 8g. Resolving it in the left and right direction, P is equal to mu r, because it's not moving. Mu is a half, R is 8g, so P is 4g. Okay? Simple, very, very simple, that first one. This is where things, I think, get a little bit more interesting. So for part B here, we are now talking about something slightly different. The force P acts at an angle of 60 degrees above the horizontal. So I'm just going to redraw the diagram for a second. Still got my 8g. I've still got my normal reaction. This time I've got P, and it is 60 degrees above the horizontal. I'm just going to give you 30 seconds to decide which forces will have changed here. I just want you to have a think to yourself. You can talk to someone about it. By making P move upwards like this, are there any forces that have changed, and what consequence will that have on this problem? So just have a little think to yourself. You can talk, or you can just think to yourself. Yep, we still want it to be in equilibrium. Okay. Any ideas? Niad, have you got any ideas about what force might change that we've got so far? Now that we've tilted P upwards, are there any forces here that you think might have changed in size? Pardon? No. Janet or Ahmed, did you decide what you think might have changed here? Yeah, when P goes up, what's going to change? Friction is going to change, but why is friction going to change? Good, because R is going to change. Have a think about this for a second. We've now got an extra force coming up here, which is P sine 60, and along here we've got P cos 60. So the value of R, has R increased or decreased? R has decreased. So because R has decreased, what's happened to the friction? It's also decreased, because remember, the friction is related to the normal reaction. It's not related to the weight, it's related to the normal reaction. So R changes, which means friction changes. This is a classic kind of thing. People will see these questions and they will have, earlier on in part A of the question, they worked out what R is, and they will just do the whole question using R is 8G. But it's not 8G. It's changed. So we have to rework out what R is, then we can work out what P is and all these different things that we've got as well, okay? So I'm still going to put that there's going to be some friction here, which is mu R, and I'm going to just quickly work out what some of these forces are. And this is where you'll need to be careful with just making sure you write these things down really clearly. Shall I do an extra diagram? No, I'm going to be lazy, okay? So my forces going up, if I resolve in the up and down direction, I have R plus P sine 60 is equal to 8G. So the normal reaction is 8G minus P sine 60. When I go left and right now, it's still in equilibrium. It's still in limiting equilibrium because it's not going to be moving at all. Let's find out what it would be. What would be my left and right forces, Amara?
Mu R and then P cos 60.
And P cos 60. Okay, now mu is a half and R is this thing that we've got here. So I can say a half multiplied by 8G minus P sine 60 equals P cos 60. This equation that I've got here is a single variable equation. What do you think I mean, a single variable equation? There's only one unknown. The only unknown that we have in there is P, so we're just going to solve the equation. So let's actually just finish this question off by finding out what P is. I'm going to try and keep this as neat as possible. So let's expand this. I get 4G minus 0.5P sine 60 equals P cos 60. What's the best way of solving this kind of equation? What do I need to do? P on one side and then P on one side, factorize and divide. So I get 4G. I'm going to be a bit sneaky here and do it as quick as possible. I'm going to factorize and put it on one side. So I get cos 60 plus 0.5 sine 60. Hopefully you can spot what I did there. I added the 0.5p sine 60 over here, and I factored out the p. So I get left with this. So p is equal to 4g divided by cos 60 plus 0.5 sine 60, which is 42.0 newtons. Okay? So this is so important, and I guarantee I'm going to ask you a question at some point, and I'm going to be like, but the normal reaction changed, so the friction changed. So you've got to do everything again. Okay, you do actually have to do everything again. It sounds like such a tiny little change. Oh, well, let's just change P. Let's just change it to 60 degrees. You're like, oh, cool. That won't be much work. You actually have to do the entire question all over again. So just be aware for looking out for that, okay? Yes? Yeah, P has changed. Oh, because 4G that we have here, 4G is not 42. I think it's, how much is it? 39.2. So this is actually 39.2. So P has changed, but it's kind of hard to predict how P will change, and it's going to depend on the angle whether P will get bigger or smaller, because when R changes, friction changes, P changes, everything all changes, like, and it's hard to predict. But yeah, the P has definitely changed in part A and in part B here, okay? One more example, and then it's just, I think we'll probably finish up. We might not have time to do any practice, but you can do some of the practice at home for me. So if there's any questions here, you better make sure you're asking me, because I'm going to send you away to do this, just having looked at these ones, okay? Right, last one then. Can I go on to the next bit, or is anyone still writing? Okay. A box of mass 10 kilograms rests in limiting equilibrium. There we are, coming across that phrase yet again, on a rough plane inclined at 20 degrees above the horizontal. Find the coefficient of friction between the box and the plane. And then we get something new that is happening. So let's just pause at this part A, and let's draw what's happening. 20 degrees, 10G, R. Right, it's in limiting equilibrium. It's a rough plane. Which direction does the box want to move? So friction, great. It wants to move down, friction goes up. So this should be pretty easy now to find out the other forces. I'm going to take this 10G. Let's do a different colour to try and make it a bit clearer of what's going on. Split it into these two. 10G cos 20, 10G sine 20. Quick little extra diagram, because I've not been very good at doing those today. R, mu R, 10G cos 20, 10G sine 20. What do I want to find out first? Up and down, left and right? I want to find out R. So very quickly, going in that direction, I can see that R is equal to 10G cos 20. And then resolving in the left and right direction, because it's in limiting equilibrium, these two things must be equal to each other. So I get 10G sine 20 is equal to mu multiplied by R, which is 10G cos 20. So what's mu equal to? What's mu equal to? You can do it just an exact value for me. Tan 20, because the 10Gs will cancel. Sine divided by cos is tan. So you get tan 20, and what did you say tan 20 was? 0.36, okay? But I just want to use tan 20 later on, so it's better to have the exact value if we can do. So we've got the value of mu. Whoever's phone is just constantly vibrating needs to put it on like do not disturb or like turn it off, because it's really winding me up. So off now. Who is it then? I don't want to hear the noise at all. It's disruptive to the whole class. Okay, this is where the question gets interesting. So this is the part of, I know it's the last lesson of the first week back, we're all exhausted, but this is the most important part of the whole lesson, okay? So you need to make sure that you're paying special attention here. Habib, this way. So it says, a horizontal force of magnitude P newtons is applied to the box. Given that the box remains in equilibrium, find the maximum possible value of P. Okay, so first of all, it's a horizontal force. Flat, not going up the slope, but flat to the ground. And it wants it to be the maximum possible value of P. Now, they haven't told us if it's pushing it in this direction or in this direction, if it's a push or a pull. You can disregard one of those. Which ones can you disregard, and why can you disregard it? It has to be a push, correct. Why? Because it's already trying to move down, isn't it? If you pulled it, it's going to start moving down. So obviously it's not going to be wanting to move down, because we've said it's currently in limiting equilibrium, about to move down. So if I pulled it down, it's no longer going to be in equilibrium. And we want it to remain in equilibrium. So I'm going to have to do, rather annoyingly, I'm going to have to do another diagram for this question. And this time, there's going to be an extra force. I've still got my normal reaction, and I've still got my pushing force that's coming in as my extra force, and I've got my 10G that is happening here. This is 20 degrees. Now, you need to pause for a second, and this is where questions in mechanics, you can't just dive in and do the same thing that you did last time. You have to stop and you have to think. Now, if you want P to be its maximum, I want you to imagine that you are that person pushing the block up the slope. And you're pushing it as much as possible so that if you pushed it any more, it would start moving. I want you to now imagine that you've pushed it a little bit too hard. What's happened to the block? It's gone up. As soon as you start thinking about it's gone up, what should you be thinking? Friction has changed now. It's no longer trying to go down the slope. We've been pushing it so hard in this direction that if we pushed it any harder, it's going to move up, which means the friction is going in the other direction to that. So it's going to be hard for me to include this on the diagram, but actually there is also friction has switched direction, okay? I'm going to highlight this to make this so important. Friction was going like this. Friction is now going like this because we're talking about the maximum value that the value of the push can be. Obviously, if we're talking about a max value, it's pushing so hard that the friction is now trying to go in the other direction. Say that again, what do you mean?
That's the only reason that it says maximum.
That's the only reason it says maximum possible value of P.
So that we make that conclusion.
Yeah, maximum possible value of P means it's pushing so hard, it's going to start going up the slope. The minimum possible value of P is just 0, because if there's no pushing force, it doesn't move. We already have seen when there's no pushing force, it doesn't move. So we're going to do this question really fast so we can get you finished on time. We need to resolve some forces. Well, previously, we'd already done these two, haven't we? So that's not going to be much bother. 10 cos 20, 10g sine 20. But the P is the one we need to be careful of. Remember, we know what this angle at the top is because of alternate angles. It's 20. So you've got this force, P sine 20. And you've got this force, which is going up the slope, P cos 20. And if ever I've seen one, this is one that requires another diagram. This is a messy looking kind of thing we've got here. So I'm going to take a bit of space for this. Upwards, I'd say take a bit of space. I always do them too close to the other diagram. So let's actually take some space. Upwards are to the right. What have I got? Shout out, please. Anything else? Nope, okay. Downwards? P sine 20 and, whoops, 10g cos 20. Left? Anything else? And 10g sine 20. Like, let's double check that we've got all the pairs. Yep, and yep, they didn't need resolving, so they're good to stay there, okay? This is now where you just need to do a lot of algebra, because it's the same thing as before. Which one do you want to find out first? Up and down or left and right? Always up and down. We always want to find out what R is. So if I resolve in that kind of direction, like this, we can see that R is equal to P sine 20 plus 10g cos 20. Now I can resolve in the left and right direction, and I can see, because it's still in equilibrium, P cos 20 is equal to 10g sine 20 plus, what was mu? Tan 20. Remember we worked out what mu was. So it's plus mu r, but instead of mu r, I'm going to say mu r. What kind of equation? Single variable, okay? There's only p in there. Everything else is a number. Okay, so we're going to just do the same technique that Amara said before, which was get P all onto one side, factorize, and divide. So I'm going to take a little bit slower than I did before. So I've got 10g sine 20. These are all horrible, horrible numbers. P sine 20 tan 20 plus 10g cos 20 tan 20. Now, some of these are probably going to simplify, aren't they? Which one of these is going to simplify? The second one, tan 20 times cos 20 is sine 20. All it's going to save you is a bit of ink and a bit of time on your calculator. So we can simplify it if we want to. Let's get them all on one side. So I've got P cos 20. I'm going to now subtract this. Minus sine 20 tan 20 is equal to 10g sine 20 plus 10g Oh, this is also sine 20, isn't it? But we're putting it on our calculator, so who cares? We're then going to do that, divided by that, and we've got our answer. And we're done. Let's just see if I've got the answer. It is 82.2 newtons to 3 significant figures. So they absolutely, stop guys, they absolutely love these questions of maximum values of things. You have to pause, you have to say to yourself, if I'm pushing it as hard as possible, the friction has changed. They love these questions where halfway through the normal reaction changes, and because the normal reaction changes, the friction changes. And even more than that, they love it where the friction changes direction halfway through the question, okay? What was I going to say to you about this before I finish up? You just got to think carefully about these kind of things. This will also come up when we do some topics in the future. We're going to look at like ladders against walls, and it will be like someone at the bottom of the ladder, like pushing the ladder without it moving, and like someone pulling the ladder without it moving to find out maximum and minimum values. Friction will switch around then. So this idea will come back in the future. So keep it in your head, okay? It's going to be there. Your homework is this. Exercise 7C, odd questions, Wednesday, please. I'll put it on Padlet. Happy weekend.